organize this for here. I don't really consider myself a non-commutative geometer anymore, so I always get surprised when I get invited to these things. But it's been surprisingly productive for me. It's been really, really good. I've really enjoyed it so far. So this is joint work with Duwenig, and the void will be this in 1 second. So the results I'm going to talk about are true for locally compact Hausdorff groupoids. You don't necessarily need a tunnel. Our system is sufficient. You don't need matching unit spaces, if you know what that means. But I will just give you the definitions for discrete groups because it's already pretty heinous as is. But always keep in mind you can do this for groupoids. Okay, so this is the outline. I'm first going to do just remain in groupoid land, talk to you about the Zappa-Szép product of two groups, and going to tell you about an imprimitivity theorem that Boyu and I proved. And then we're going to move that to C-star land. I'm going to tell you what our C-star analog of the Zappa-Szép product is within C-star land. But for that, I have to first motivate Hell bundles a little bit. And then hopefully at the end, I'll have some time to talk about some theorems we proved about our new construction. Okay, so let's pretend we are back in our first class about algebra. Given two groups, you take the Cartesian product and make a new group. You define multiplication component-wise, you define inversion component-wise, and you get a new group. So it's all very nice. But we can also take a step back and ask for one of our groups to act on the other. And just explicitly just saying to act on the space G at the moment. And for me, my left action of H is going to be blue, just so that you can keep track of what's happening. And my little triangle is pointing towards the thing that is being acted on. So just as a visual reminder of what's happening, I also have this little thing here up here, if you ever forget what's what. Okay, so we have this action on the left, and we want to make a group that encodes that action. Again, as I said, take the Cartesian product. And this time, my multiplication is defined like that. You've all seen this before, I know, but I remind you just because it eases you into the next step. So here we pay a price for H1 jumping over G2. And for this to become a group, we need to adjust our inversion formula. Okay, so I want this to actually be a group, so I need to ask for more. I can't just have any action. I need to actually act by homomorphisms, right? I need to have homomorphisms, so I need that H acts on a product by acting on the first and then acting on the second. Okay, in this case, we get the semi-direct product. Okay, so you probably, by the look of this, already know what's going to happen now. I'm going to take another step back. And this time, my two groups actually act on each other. So H acts on the left, G acts on the right. And I would like to make a new group, described with this little bow tie symbol here, which I colored purple, red and blue, which encodes both of these actions. This time, I want everything to be symmetric. This means that now I not only pay a price when H1 jumps over G2, but also a price when G2 jumps over H1. So it's really just a symmetric type of thing, and you have to adjust the inversion. Now this time, again, for this to be a group, I need associativity, and to get associativity, I need to ask for this different type of condition. I'm not acted by homomorphisms anymore. Instead, if my H acts on a product, it's the same thing as first acting on the first one, and then this variant of it acting on the second one. So you really need this condition to make this group multiplication be associative. And I have a similar condition on the right. You don't have to remember this condition, just keep in mind when I say compatible, I mean whatever I need to make a group. And this guy is then the Zappa-Szép product. Just as a reminder, at the very bottom, one more time, automorphism gives me semi-direct product, compatible actions gives me the Zappa-Szép product. That's the takeaway from this. Okay, so these types of two-way actions are pretty fashionable. People are working on them. We've seen some of them before as well. So for example, in the self-similar groups, a la Nekrashevich, we have some finite set, we have a subgroup of the automorphism group of words. And this is self-similar if whenever I have H acting on a word that starts with X, it's the same thing as acting on the letter X and then having a variant of H acting on the rest of the word. There are self-similar actions on directed graphs and on K-graphs. There are Zappa-Szép products of semigroups and of groupoid, and here this W is Mike's W. And so these things really, they're quite interesting. People are working on these sorts of stuff. Now, you might wonder, like, how do I figure out whether something is a Zappa-Szép product? There's this nice little fact that if you're given two subgroupoids or groups of a group, and you know that every element of the big one can be written uniquely as a product GH of the subgroups, groupoids, then your K actually is a Zappa-Szép product of these two substructures, and you figure out these two actions by looking at what happens if you multiply H by G. You know, by this uniqueness condition here, H times G can always be written as something in G and something in H. And this is exactly how these actions are. Okay, so there's surfactors repeated. If you have two subgroups that uniquely decompose your group, then you are a Zappa-Szép product. An example would be the n by n invertible matrices, which, because of the QR decomposition we supposedly at one point learned about in linear algebra, you can always decompose as a unitary matrix and a nice enough upper triangular matrix. Another example, if you start with two commuting surjective local homeomorphisms on some space, and we assume that they are star commuting, which means they commute in a very strong sense. So whenever you have an element that can be written as the image of under T and as the image under S, then it has to already have come from the fact that T and S commute. So this little x here actually is an SZ, and this little y here actually is a TZ. If you have this additional condition on your commuting surjective local homeos, then the diagonal-Renault groupoid that you get from these two, so that's this guy here, if you know what that means, actually is a Zappa-Szép product of the two individual diagonal-Renault groupoids. So just as an example. If this doesn't tell you much, that's fine. Okay, I just wanted to motivate that these things exist. Okay, so now we can get to a theorem. First, let me, as always, recall things in the world that we are all familiar with, semi-direct products. So this is originally due to Green, and then a generalization by Kalizewski, Muley, Wigan, Williams. We start with two groups, and we have a groupoid. These two groups act on the sides of the groupoid. If these, the action, say I've now picked one, I picked the K action on the right, if that is free and proper, then you can actually make the quotient by the action a locally compact Hausdorff groupoid. If that action commutes with the left action, the quotient actually also gets the left action. If that left action is by automorphisms, then so is this action. And so, as I mentioned earlier, if you act by homeomorphisms, the semi-direct product is actually also a groupoid. And then if you have all of these things for both things, so not just for yellow and blue, but for blue and yellow, then actually these semi-direct product groupoids are Morita equivalent. So that's a standard fact. And as an example, if you have that one of the two groups that are acting is trivial, say K, then you get that the semi-direct product is Morita equivalent to the quotient, right? Which is one of the motivating things when we look at semi-direct products, because sometimes quotients are not very well behaved. The second corollary is that as long as you have R systems floating around, the C-star algebras of these are Morita equivalent. An equivalence of groupoids actually induces Morita equivalence of the C-star algebras. Okay, so now I'm going to take this, I'm going to take a step back and generalize this to Zappa-Szép products. And after you've seen that, it might not be so surprising what I will have to do. The first thing I do is actually, I let everything be groupoids. I don't just have groups acting on a group, I can actually just take all of them into groupoids if I want to. And this time I have multiple actions, not just H on G and K on G, but G also acts back. Again, free and proper and commuting tells me the quotient is a groupoid that has an action. That remains the same. This time, I also ask for the K action on G to leave the G action on H invariant. And if you do that, then you also get that this quotient here that you have on this side acts back on H. Now, I mentioned earlier that for the semi-direct product, we needed actions by homomorphisms. For the Zappa-Szép product, we needed compatible actions. And so here, my next line, where I said, if I act by autos, I get a groupoid, and replace that with, if I act compatibly, then I get a groupoid with Zappa-Szép product that encodes both of these actions. And again, if the situation is symmetric, you get that the two Zappa-Szép product groupoids are actually Morita equivalent. And again, you get the same type of corollary. The Zappa-Szép product is equivalent to the quotient, and these two C-star algebras are Morita equivalent. Okay, wonderful. Our first little groupoid theorem. So here, just a reminder again, if you have two groupoids acting compatibly in a nice way and free and proper, you get this equivalence of two groupoids. And let me give you an example. I go back to the setting that I had before. I have these local surjective homeomorphisms that are not just commuting, but actually star commuting. So this is a very strong type of commuting. And in that case, I can take G to be the Diacono-Renault groupoid from one of them, H to be the other one. And then you can check that this is the Diacono-Renault groupoid we looked at earlier, which is the Zappa-Szép product of G and H. And it's an equivalent to this other Diacono-Renault groupoid, where here this X mod tilde T is the modding out by the equivalence relation generated by T. And that is the induced action from S. I should mention, though, that the word certain here, so I need some extra conditions, and at the moment they are rather restrictive. We are still working on generalizing this a little bit, but at the moment we don't have many examples for this, but there are at least some. Okay, so moving on from groupoid land to C-star land, because maybe groups are not your thing. So let me just remind you one more time. I'm going to repeat myself a lot, because otherwise people get lost, I think, with all the symbols floating around. In group land, left action by autos gave us the semi-direct product, was this structure. And we know what happens for C-star land in this case. So we know exactly what the C-star algebraic analog of the semi-direct product is. Maybe the cross product, right? So we take our group acts on a C-star algebra by star automorphisms. We get a C-star algebra A R times H. And this time multiplication is defined by that formula. And if you look, it's exactly the same formula. Right? So I take an element A delta 1, so this is a point mass of H1. Remember, I pretend that I have just discrete groups, right? So make everything a little nicer. And it multiplies with this other point mass like that. So the point masses really just multiply, but this H1 has to pay a price when it jumps over A2. So this is the action. And likewise, involution mimics what happens with inversion. I have H inverse act on A star. So now, the Zappa-Szép product, this was the generalization of this setting here, where we have two actions. And the question that Boyu and I asked ourselves was, if the semi-direct product in group land becomes the cross product, then what is the Zappa-Szép product? So what does that become in C-star land? And in particular, what does it mean for A to H, act back on H, right? Because you need a two-way action, not just a one-way action. And then once we have figured out what it is, what results can be generalized from the cross product to our new. Okay, semi-direct product becomes cross product. What does the Zappa-Szép product become? One solution that we had is that instead of just looking at the C-star algebra, we actually look at a Fell bundle B over G. And then we use the fact that G acts back on H and use that to induce a C-star action back on the group. So if you haven't seen this, let me give you a definition of Fell bundles. I'm not actually going to define much. I'm just going to give you an idea of what a Fell bundle is. So a Fell bundle over discrete group G is a family of Banach spaces indexed by your group. These are my Gs. And it comes equipped with extra maps, namely multiplication. For every G1 and G2, I have a map that maps the fibers of these two to the fiber of the product. So I can multiply fibers. And evolution maps. I can go from the fiber over G to the fiber over G inverse. And these maps satisfy lots of different properties, which are kind of analogs of C-star algebra properties. So for example, if I take an element in the fiber over G, and if I look at its norm in the Banach space BG, then this should have this relation with the norm of B star times B. This is now in the fiber over the identity. So you have properties like that. One fact is that the fiber over the identity element is actually a C-star algebra, and all of the other fibers are imprimitivity bimodules over that fiber. So Morita equivalences. So for the people who went to the school last week, Ram introduced right-Hilbert modules, and these are actually bimodules. So they have the right-Hilbert structure and the left-Hilbert structure that plays nicely together. And again, a reminder, actually you can do all of this for locally compact Hausdorff groupoids. It just becomes very messy. This is why I pretend like everything's discrete and you don't have to worry about all of these local structure. Okay, so from a Fell bundle, like the one I've given you, I've defined in the last slide, you actually can build a C-star algebra. Not just one, but let's just focus on one. What you do is very similar to how you construct a C-star algebra out of a group or groupoid. You start with functions from G into your bundle that are actually sections. So at a point G, it gives you something in the fiber over G. You want these to be compactly supported. Yes. And then you equip that thing with a convolution and an involution. And the formula is exactly like the one that you know from a group C-star algebra. So you go through all elements in your group, and then you evaluate your sigma at that element, your tau at element inverse times the thing you started with, and then you multiply them. And involution, likewise defined. So here, important, this is the multiplication of my Fell bundle, this is the involution of my Fell bundle, right? It's not just easy to do something complicated. And then you complete that thing to get a C-star algebra. Again, one more time, this here is the Fell bundle multiplication. This is where the interesting stuff happens, right? So while this formula might look simplistic and might look like it's just the one from group C-star algebras, there's actually a lot of stuff that you can hide in here. We'll see that on the next slide too. That's what I'm going to tell you. Fell bundles are really versatile. So even if you don't care about anything else in my talk, please care about the next slide. Okay, so here again, the definition of a Fell bundle, we have these multiplication maps, and we have this involution map, or multiple of them actually, and we get a C-star algebra by completing the continuous sections. So let me give you some examples to show why you should care about Fell bundles. The most simplistic example, I start with a trivial group, and I just have a C-star algebra as a fiber. That's the only thing I have. I let the multiplication be the C-star algebra's multiplication. I let the involution be the C-star algebra's involution. This time the sections are just the C-star algebra, and the C-star algebra that I get is just the C-star algebra I started with. Nothing interesting has happened. Okay, but I can do this for group C-star algebras. This time I let my fiber over G, G being a group, just always the complex numbers. So the most simplistic thing you can think of. This time, my multiplication is just multiplication of the complex numbers. My involution is just involution of the complex numbers. My continuous sections are just functions on G, and the C-star algebra is the group C-star algebra, or groupoid C-star algebra. At this point, you might wonder, what if I want the reduced one? And you can also do this for the reduced. So there's also a way to construct a reduced groupoid, Fell bundle C-star algebra that also exists. I just care about the full one. Okay, maybe you think group C-star algebras aren't interesting enough. What about twisted group C-star algebras? You can do that too. So I start with the group again. I again just let my fibers be the complex numbers. This time I assume that I also have a 2 co-cycle. So this is a map from G times G to the circle that satisfies a nice two-core cycle condition. Now my multiplication has to become a little more interesting. Instead of just multiplying complex numbers, I actually also multiply by the co-cycle that picks up over which fibers I was in. And likewise, my involution also picks up the G, like so. And if you give your bundle of complex numbers this multiplication and this involution, you get the twisted group C-star algebra. And at this point, if you're interested in in groupoids rather than groups, and you might be interested in twists that are more general than two co-cycles, yes, general twists can also be encoded in Fell bundles. And then the example that we started with earlier on, I can also have non-trivial fibers, right? My fibers so far have always just been the complex numbers. Instead, start with a C-star algebra that is being acted on by automorphisms for G. My fibers are all the same C-star algebra the whole time. This time, my multiplication in my Fell bundle is the one that pays the price, right? So if I multiply A1 and A2, it's not just the C-star algebra multiplication, but instead A1 pays the price of what fiber it's in, or A2, I guess. So here, this one picks up what fiber A1 is in. And likewise, my involution pays a price. And if you do this, not surprisingly, the C-star algebra of this Fell bundle is actually the cross product. So just to reiterate, my input C-star algebra, I can get a C-star algebra. My input a group, I can get a group C-star algebra. My input a twisted group C-star algebra. A dynamical system, the cross product. So I hope that I have explained why Fell bundle C-star algebras are actually everywhere. You might actually want to learn about them. And let this be the absolute minimum to take away from this. Right? Okay, so you've now had a steep introduction into Fell bundles. And now I can actually give you our definition of the Zappa-Szép product within C-star land. Are there any questions at this point? Okay. I risk that I repeat myself, but we started with the semi-direct product in groups becomes subproduct. And so what does the Zappa-Szép product in group land become in C-star land? What is the backwards action of A on the group? Okay, so here are my formulas again. In group land, I had this group multiplication. I copied that into C-star land like this. So I took this formula and I just did this most simplistic thing I could do. This gives me my cross product. I took the inversion formula, made an involution formula out of that. Now, in group land, we were interested in this compatible setting where I actually have two actions. And here, my multiplication has become a bit more interesting. And then my inversion has become a bit more interesting. So now, I had to replace homomorphism by compatible. If I want to do this in C-star land, I will have to do the same thing. This time, I'm letting my H act on a Fell bundle B. This Fell bundle B actually lives over the G that I have going around as well. And I want to construct a new Fell bundle, which I give this nice little symbol so that you can distinguish it a little bit. And I want that over the fiber over G comma H within my Zappa-Szép product of groupoids, I want that the fiber really is just the original fiber over G. So fiber-wise, I don't really change my bundle. The main thing that I have done is I have created a lot more of the fibers. And this, basically what is happening here is that I'm thinking of H or maybe the C-star algebra of H as the trivial line bundle with fibers, the complex numbers. And if I take a Banach space and tensor product it with the complex numbers, I just get the Banach space back. So I don't change the space. Now I take the formulas down here that I had for the cross product. I realize this actually came just from the semi-direct product. That was my motivation for defining that. Now my motivation is to define a product that mimics the Zappa-Szép product. These are the formulas up here. And so what I do is I literally copy paste and replace every G by a B. Right? So I've really done nothing but take this formula and repeat it down here. So what happens now? I have an element in the, say, G1H1 fiber of my new bundle. So this is just something in the fiber over G1. I multiply it by something in the fiber over G2. And my formula looks like this, copy paste it from there. What have I done? I have taken the product not just of B1 and B2, but actually of this changed version of B2. And here is the Fell bundle multiplication of my original Fell bundle. On the H part, I do the exact same thing. I let B2 act back on H1. And what I mean by this is really whatever fiber B is in, it's in the fiber over G, say, let G act on H. I do the same thing for the involution. I copy paste the formula. Every inverse that doesn't make sense becomes an involution. And again, I just have, oh, sorry, this here should not be an inverse, this should be an involution. Copy pasting is sometimes a bit dangerous. Okay. Here, now to make a point again, this little symbol, so the H1 being acted on by B2, this is where we make use of the fact that we have a bundle. This is where we make use of the fact that my B here has fibers over G, and I know how G acts on H. And so this is what replaces the A has to act back on H. Okay, so I swept under the rug what this compatibility condition is that I needed, but you might not be surprised that I tell you it just is copy-paste the conditions you needed to make the Zappa-Szép product work. So what I mean by that is, for the Zappa-Szép product of the groups, I needed that if H acts on a product, it's the same as if it acts on the first component and then this variant acts on the second component. And for my action of H on my bundle, I ask for the exact same thing. I want that if H acts on a Fell bundle product, it acts on the first one, and then I multiply with this variant acting on the second one. And you do this for all the conditions that you asked for in the original definition. And then, I have already alluded to this, if you are in the setting, so you have a Zappa-Szép product of groups, you have a group acting on a Fell bundle in a compatible way, in this sense, actually groupoids, then this thing that I constructed on the last slide actually is a Fell bundle, and it's a Fell bundle over the Zappa-Szép product. In our first paper, we called this a Zappa-Szép product. We have since moved to a self-similar product because we are a little more general than the original Zappa-Szép product definition. Okay, so here's my theorem one more time. I have this nice groupoid action G on H. I have one on B. I have them compatible. I get a Fell bundle. So you might have seen results like this in the literature. There is a result, for example, if you have an appropriate left action on a Fell bundle, you get a semi-direct product Fell bundle, and ours generalizes that, right? So the construction really, they're very compatible, these two things. Now, you can see what happens if you have like an iterated construction. So say we have these two groupoids acting on each other, or groups in this case. I have an action of the Zappa-Szép product on some C-square algebra. That's my input data that I start with. In this situation, the Fell bundle you get for this dynamical system can be decomposed as a Fell bundle of the restricted dynamical system, Zappa-Szép product, the rest. Just as an example. So our construction is quite natural in a sense. In particular, if you look at the dynamical system that is constantly the complex numbers and you have actually no action whatsoever, in this situation, what this here means is that the trivial line bundle of the Zappa-Szép product is the same thing as the line bundle of G, Zappa-Szép product of H. So this is really just a sanity check. Have we done something stupid? No, I hope we haven't. And this is, I should mention, also true for groupoid dynamical systems, which are a bit more common. This still works. Okay, recap one more time. We started with groups. No action gives you the Cartesian product. One action by automorphisms gives you the semi-direct product. Two actions which are compatible gives you the Zappa-Szép product. We moved this into C-star land. No action is just the tensor product of the C-star algebra by group C-star algebra. One action by automorphisms gives you the cross product. two actions on a Feld bundle, compatible actions on a Feld bundle gives you the Zappa-Szép product C-star algebra. And now the question remains, what sorts of properties does this thing share with this thing? So which sort of theorems that we know about the cross product can we generalize to our new Zappa-Szép? Okay, so let me give you some examples. You might remember that there is a nice notion of representations for a dynamical system. So a covariant representation for an action by automorphisms on a C-star algebra is a representation of the C-star algebra and a unitary representation of your group on the same Hilbert space, which satisfy this condition. If you want to move the unitary past the representation of the C-star algebra, you have to pay a price. And then there is this old theorem that tells you that covariant representations of this on this side for the dynamical systems and star representations of the cross product are actually in one-to-one correspondence. So you can integrate representations of the system and disintegrate representations of the cross product. Take a guess what I'm going to do next. I'm going to take a step back and make this definition for two actions. So the new definition is a covariant representation of a system where H acts compatibly on a Feld bundle, consists of a representation of the Feld bundle and a unitary representation of my group, such that, yeah, okay, originally I had to pay one price, this time I have to pay two prices, right? So everything just becomes symmetric. That's the main thing that happens with the Zappa-Szép product. So not only does my H act on B, but also the fiber that B lives over acts on H. And you might be wondering, why do I still have that theorem up? Because a generalization where that works too. So representations of this sort are in one-to-one correspondence with representations of your C-star algebra, this Feld bundle C-star algebra. So you can integrate them and disintegrate them. And I should one more time point out, like I'm being a little bit schizophrenic here about group and groupoids. You can also do all of this for groupoids. It's just very messy, right? So groupoids representations are just not very pretty. And here are Feld bundle representations for groupoids. Okay, the question remains: what other things do we know that our new C-star algebra might share with the cross product? One, I suspect, motivating example for Excel's definition of C-star blends are cross products. If you have an H action by automorphisms on a C-star algebra, then the C-star algebra and the group C-star algebra give you, together with the cross product, gives you a C-star blend. We have seen this is work by Mike and his collaborators, that if you have a Zappa-Szép product of groups, or groupoids actually, then the C-star algebras of the two groupoids and the C-star algebra of the Zappa-Szép product is also a C-star blend. So it's a, you have one big C-star algebra, so this is in this case the cross product, and two sub-C-star algebras that have injective homomorphisms into the multiplier algebra. So these are the ones that I have these little arrows here, such that if you look at the image of the tensor product, it is exactly the small C-star algebra that we started with, not the multiplier algebra. I hope I got that right. And then we checked that at least when your unit fiber is a unital C-star algebra, you have the exact same type of statement. So if you are in the setting where the C-star algebra of where the Zappa-Szép product makes sense, then it is a C-star blend of the Feld bundle C-star algebra and the groupoid C-star algebra. Okay, so now let me remind you that in group land we had this nice little impermittivity theorem. Here I had my actions, two-way actions H and G and G and K, which are compatible, free, proper, and leaving the backwards action invariant. In that setting, I got that the quotients are actually groupoids. I got that on these quotients I have compatible actions so that I can look at their Zappa-Szép product. And I had that the Zappa-Szép product are actually equivalent groupoids, and in particular their C-star algebras are therefore Morita equivalent. Now you can guess what happens next. I'm going to bootstrap this to the case of Fell bundles. So suppose you are given two groupoids H and K, and you're given a Fell bundle over another groupoid G. And suppose we are in a setting where I can make sense of my Fell bundles of a Zappa-Szép product. Meaning I have actions of H on B and of K on B, which are compatible in a nice sense, and the backwards actions of the groupoid that B lives over. I again need the actions on B actually on G to be free and proper, and I need them to leave the backwards action invariant. This time, what we have proved is that if you take the Fell bundle and quotient it out by this action of K respectively H, you get another Fell bundle, and these Fell bundles are Fell bundles over the quotient groupoids. On these quotient Fell bundles, you get actions that are compatible. You can make sense of the Zappa-Szép product. And lastly, the Fell bundles that you get from our construction, and these here should be the curly bow ties, I'm sorry, like those fancy ones. So this is the new construction that we made. These are again equivalent as Fell bundles. And equivalence of Fell bundles is a definition I definitely want to avoid. It's very, very, very intricate with lots and lots of conditions. But the bottom line of an equivalence of Fell bundles is that the C-star algebras that are equivalent as long as you have sufficient car systems floating around. So the definition of a Fell bundle equivalence is very much analogous to that of a groupoid equivalence or of a C-star algebra Morita equivalence. And again, I should point out that this result that we have proved here does generalize a analogous statement for the semi-direct product that I alluded to earlier. So this is a result that existed before, and we've done that now for two-way actions. So this leads me to actually the end of my talk, even though I have a little bit of time left. But the main thing that we are now trying to do is to figure out what our new construction remembers about the original system that we started with. And we don't know, like we haven't actually started this line of investigation, but it is a natural question to ask. Then we would like to do the same construction actually for two Fell bundles, not just for a Fell bundle and a groupoid. And in this situation, we would like that the definition that I gave you of the Zappa-Szép paragraph and Fell bundle with a groupoid should be recovered by looking at the line bundle. And so far, the obstruction that we hit is that we are not 100% sure what tensor product we should take. Like, what is the correct fiber that we want to look at? And then, what new examples of equivalences are being picked up by our construction? The main obstruction that we have so far is that really the freeness condition that I mentioned means that it's mostly interesting when you look at groupoids. When the Zappa-Szép product that you look at are groupoid Zappa-Szép products. But the problem is that these are very new. So the paper by Mike, I think it's just, I don't know, a handful of years old. And so groupoids Zappa-Szép product are just not plentiful yet. I'm pretty sure that we just have to unlock something, and then there will be examples, but at the moment we're just still trying hard to find them. So, yet. This was my last slide, but I still have lots of time. So yeah, this is not the slide. This is actually not. Yeah, so this shows you that yeah, you be happy that I try to avoid as much technicalities as I could. So this is just all the actions floating around in our paper. And here is one little backup frame from Mike. So I mentioned earlier that originally the Zappa-Szép product is defined in a very symmetric way. In particular, you ask that the unit spaces actually coincide. And this it makes sense. The Zappa-Szép product is something symmetric. But we were able to avoid that and asked for instead there just be a surjection from one of the unit spaces down to the other. In particular, we then replaced the momentum map of the H action on G. It's not the range map anymore, but instead it's the range map composed with this surjection. So this way, you unlock the situation where one of the two things can be a group and the other one is a groupoid with a big unit space. And so in particular examples in the past, when, for example, in Mike's paper, when people were trying to construct Zappa-Szép products the old-fashioned way with matching unit spaces, they needed to, when they have a group, to actually enlarge that group to the transformation groupoid acting on the unit space in order to make them have the same unit space. You can avoid that with our construction. So our construction does that by nature, basically. So our construction picks up this example. And the one big caveat at this point is, at this point, G and H are not interchangeable anymore. So there really is a distinction between which of the two is the one that has the smaller unit space. And so in the whole theorems that I mentioned, the thing in the middle, that's the one that has the larger unit space. The things that are acting on the left and right are allowed to have smaller unit space. And that will then end my talk, and I go back to that wonderful diagram.